Hi everybody, welcome back to your regularly scheduled programming. Today we are solving LeetCode number 70, which is called climbing stairs. The problem states you are climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? It gives us a couple of examples which we'll explore on the whiteboard, and it gives us a constraint of n has to be in between 1 and 45 inclusive. Our task is to find the number of distinct ways to get to n steps, and we can take 1 or 2 steps each time to get there. Let's visualize this problem with this diagram I've constructed that depicts a staircase as if you're looking at it from the side. So each block represents a step, and the step number is written on top of each step. So this is step 1, step 2, step 3, onwards. Inside of each block, I've written out the unique paths to get to that step. The 1s denote a single step, and the 2s denote a double step. Underneath the red line, I've just tallied up the number of unique paths to get to that step, and I've just written it out. Finally, we have in black at the bottom the difference between the total number of paths for each subsequent step. So for example, for step 3 we have 3 ways of getting there, for step 4 we have 5 ways of getting there, and the difference between the total number of ways of getting there for each step is 2. So let's start off with step 1. The only way to get to step 1 is to take a single step. We can't take a double step because then we would have ended up at step 2. So from 0 to 1, we can just take one step, and there's one possible way. Let's explore the total ways of getting to step 2. So we can take a single step twice, or we can take a double step once, and there's 2 unique ways of getting there. For step 3, we can take a single step thrice, or we can take a single step followed by a double step, or we can take a double step followed by a single step, and there's 3 unique ways of getting there. And we can continue this for however many steps we need, but we can see that it gets increasingly tedious writing all this out and more difficult to figure out the paths. Let's try and figure out some sort of pattern from the rest of this chart that we can use to solve the problem. Let's take a deep dive into the differences we've calculated here. So for step 5 we have 8 ways of getting there. For step 6 we have 13 ways of getting there. 13 minus 8 is equal to 5. Let's do that for steps 4 and 5 as well. So for step 4 we have 5 ways of getting there. For step 5 we have 8 ways of getting there. 8 minus 5 is equal to 3. And we can apply this to all the other steps. If we take a deeper look at that, we can actually see that the difference between any 2 steps is actually equal to the total number of ways to get to the previous step. So the difference between steps 5 and 6 is equal to 5, and that's equal to the total number of ways to get to step 4. The difference between steps 4 and 5 is equal to 3, and that's actually equal to the total number of ways to get to step 3. And this holds true for all the other steps as well. So this means that if we actually have some reference to the difference, we can rearrange this formula. So instead of subtracting 8 from 13, so 13 minus 8 is equal to 5, we can do 8 plus 5 is equal to 13. And what this means is that we can calculate the total number of ways to get to any step we want. So for any step n, it's really just going to be the sum of the 2 numbers before it, because this 5 is the number 2 numbers before the nth number, right? If n was equal to 6, then it's really just the sum of n minus 1, which is this 8, and n minus 2, which is this 5. And 8 plus 5 is equal to 13. Let's explore a couple more just to confirm. So if n was equal to 5, then it would be the sum of the 2 before it, so 5 plus 3 is equal to 8. And then last one we'll explore is if n was equal to 4, then it would be the sum of the 2 previous steps, and that's 2 plus 3, and that's equal to 5. So this does hold true. And we can create a formula from this. So to find the total number of ways for any step n, it's equal to the summation of the total number of ways for the n minus 1th step and the n minus 2nd step. And this is actually the same formula used to calculate numbers of the Fibonacci sequence, which we'll explore in a minute but put to the side for now. I've written down a few pieces of information here that really help me fully grasp and understand this question, and I hope it can help you as well. The first point is our last known position can only ever have been the n minus 1st or n minus 2nd step, and this is because we can only take 1 or 2 steps at a time. If n was equal to 5, the only 2 places where we could have come from are either the 4th step or the 3rd step, because these are the only positions where we could have taken 1 or 2 steps to get to 5, or n. The next two are connected. So the first, and I'm going to use this example down here to demonstrate. So the first principle here is the n minus first step covers all the ways in which our final step to get to n is a single step. I'll demonstrate that real quick here with if n was equal to 5, then the n minus first step is going to be equal to 4. And this should cover all the ways in which our final step to get to n is a single step. So if these are all the ways to get to 4, then and I know the only way I can get from 4 to 5 is to take a single step, then all of these ways plus a single final step are a way to get to 5. The second point is the n minus second step covers all the ways in which our final step to get to n is a double step. Let's explore this example here of n equals 4. So this diagram is the same as here, just shrunk down for steps 2, 3, and 4. So let's first explore the first law, which is the n minus first step covers all the ways in which our final step to get to n is a single step. So looking from 3 to 4, let's write down all the ways we can get to 3, 1, 1, 1, 1, 2, and 2, 1. Now, we can just add a single step at the end, which is the final step, to get to 4. And so this holds true. Now, the second principle is the n minus second step covers all the ways in which our final step to get to n is a double step. So if we look from 2 to 4, let's write out the ways we can get to step 2, so 1, 1, and 2, and just add a double step, which is our final step, and that also holds true. But you may argue that we can also have taken 2 single steps to get from step 2 to 4, and those are written here. And that is valid, but the only thing is that we've already considered those cases when we went from 3 to 4. So 1, 1 and 1, 1 is equal to that, and then 2 followed by 2 single steps is equal to that. So the ones that use the single step are already explored in the n minus 1th step. So these two principles hold true, and we can use that when designing our answer, because now we just take the sum of the total ways and we get 5. So 3 plus 2, 5. Now let's take a moment to talk about the Fibonacci sequence, which I mentioned earlier when we came up with this equation. So the Fibonacci sequence is just a sequence of numbers in which each number is equal to the sum of the 2 preceding numbers, and it's initialized with the first and second numbers being 0 and 1. I've written out the first 7 Fibonacci numbers here. The 2 it's initialized with are written in green, 0 and 1. And to calculate the next number in the sequence, we just take the sum of the 2 preceding ones. So 0 plus 1 is equal to 1. 1 plus 1 is equal to 2. 1 plus 2 is equal to 3. 2 plus 3 is equal to 5. And 3 plus 5 is equal to 8. This is the formula. So to find any number n of the Fibonacci sequence, we just take the sum of the 2 previous elements, n minus 1 and n minus 2. We can test that real quick with this. To find the 7th Fibonacci number, we take the sum of the 6th and 5th Fibonacci numbers, so that's 5 and 3 respectively, and we get 8. We're going to be using dynamic programming to solve this problem. The first DP method we're going to use is memoization. In essence, memoization is recursive, so we're going to need base cases, and we also make use of a memo object where we store the answer for each call. That means we only have to evaluate each call at most once, and any other instances of that call are going to be answered or evaluated using the memo, where we just reference the stored answer. Our base cases are going to be if n is equal to 1, we return 1, and if n is equal to 2, we return 2. Those are the most elementary cases. We came up with them pretty quickly over here, and they make use of the information given to us in the problem. I have a problem set up here with n is equal to 5. This structure showcases the recursive nature of this approach, where 5 recurses into 4 and 3, 4 recurses into 3 and 2, 3 recurses to 2 and 1. And basically, the answer to any node is equal to the sum of the recursive nodes. And that's in line with our formula, where the total number of steps to get to 5, or n, is equal to the total number of steps is equal to the sum of the total number of steps to get to the n minus first and n minus second step. So total ways to get to 5 is equal to the sum of the total number of ways to get to 4 and 3. So you may notice that this left subtree branches out a lot deeper than the right subtree, and that's because of what I mentioned earlier about the memo object. When I explore this left subtree fully, I'm going to evaluate f at 3 along the way, I'm going to store it in my memo object, and by the time I get to the right subtree and see f at 3 again, I'll already have that answered, and I can just reference the memo and obtain my value. So I think that covers all the details around this memoization strategy. Let's get to solving this. So I'm going to go all the way down to the deepest level of the subtree, of the left subtree, and evaluate f at 2. So the base case is if n is equal to 2, we return 2. So this is going to equal 2. F at 1, base case again, if n is equal to 1, we return 1. So these two calls, f at 2 and f at 1, are going to return 2 and 1 respectively. Now, f at 3 is going to be equal to the sum of these recursive calls. So f at 3 is equal to just 2 plus 1, and that's going to be equal to 3. And I can store that in my memo. So 3 is equal to 3. And that key, so where the key is the step number, and the value is the total number of ways to get there. Now we have 3 for f at 3, and f at 2, evaluates to the base case, and that's 2. And now f at 4 is going to be equal to the sum of 3 plus 2, so 5. I can store that in my memo, so the fourth step has 5 ways of getting there. Put some commas here. And now I have 5 for f at 4, and then f at 3. Well, I can check my memo, so it does exist in there, and the answer is 3. So that's just going to evaluate to 3. And now f at 5 is just the sum of those two. So 5 plus 3 is equal to 8. And that's my final answer. Let's talk about the time and space complexity. So the time complexity is linear O of n, and this is since each value is computed only once and stored in the memo object. Therefore, the number of overall computations is going to be linear with respect to the input size n. The space complexity is also O of n linear, and this is because the size of the memo object grows linearly with the input n as values are stored for each distinct value of n. One general note I want to make about the memo is that you may have noticed that it doesn't start from 1, and we only have values starting from 3 onwards. And that's because steps 1 and 2 are handled by the base cases, and they just return 1 and 2 respectively, and so we have no need to store them in the memo. Here is the code for our memoization approach. We have the memo initialized, and the first thing we're going to do is check the memo to see if it contains the answer to the step we're currently looking for. If it does, then just return the answer to this step. If it doesn't, then let's look at the base cases. If n is equal to 1, if it's the first step, return 1, because we only have one way of getting there. Or if n is equal to 2, the second step, then we know 2 ways to get there, so return 2. Otherwise, if none of those apply, then we're going to compute the total ways to get to this nth step, and that's just equal to the sum of the n minus first and n minus second step, and we're going to store that in our memo object for future reference, in case there's any future calls of that, in which we can just check the object at that point, the memo object, and get our answer. At the very end, we're just going to return what we have stored in the memo for this nth step. If we give this a run, we can see that it'll pass our test cases, and then let's submit it, and it passes. Let's solve this using DP tabulation now. Tabulation is iterative, and it makes use of a table that stores values. The table is going to be proportional in size to the input. So if the input is n equals 5, the table is going to hold 5 elements. This table uses zero-based indexing, so the fifth step is going to be represented by the fourth index, the fourth step is going to be represented by the third index, and so forth. Our table is going to be initialized with a couple of values similar to how we were given the first two numbers of the Fibonacci sequence. These are basically like the base cases we used in memoization. So the first step is going to be initialized with 1, and the second step is going to be initialized with 2, which we have here. Here's our formula, which is the same as the Fibonacci sequence we calculated earlier, and we can test it real quick to find the next value in this sequence. So the table at index 2 is going to be equal to the table at the I minus first index, so that's going to be table at 1 plus table at 0. These are just equal to 1 and 0, or sorry, 2 and 1, my mistake, and that's equal to 3. And that's correct. And now the next number in the sequence is going to be the sum of the two previous, so that's 5, and then 5 plus 3 is 8. The time complexity of this approach is O of n linear, and this is because the loop iterates n minus 2 times, where n is the input size. The number of iterations increase proportional to the input size. The space complexity is also O of n linear, and that's because the size of the table array directly corresponds to the input size n. It requires additional space proportional to the input size. This is the code for the tabulation strategy. The first thing we do is we initialize the table as an array of n elements. We assign the first two indexes of the table to 1 and 2, which is our most basic cases from which we can then compute the next elements in the sequence. We start our loop at the second index because we've already filled out the 0th and 1st indexes, and we fill out the rest of the table. We then finally return the last element in the table, which is n minus 1. Let's run this. Cool. And submit it. Awesome. The final way we can solve this problem is using pointers. This strategy is also going to be iterative. We'll be using n equals 5 as our example. The very first thing we're going to do is check if n is equal to 1 or 2 and return 1 or 2 respectively, because these are our base cases as discussed previously. I've drawn out a diagram of this example where I have the red underlines represent steps. So we have 5 steps. This is the first step, second step, third step, fourth step, and our answer is going to be where the 5th step is. So, as has been the recurring theme in this problem, we're not going to be able to calculate, or we can only calculate the answer or for the step we're looking for by summing the two previous values. In this case, we don't have them, and so we'll have to start, or we'll have to compute all of those values before we can get to answer. So we'll start off with the third step, because from our base cases, we know the answer to the first and second steps. The answer to the first step is going to be 1, and the answer to the second step is going to be 2. So we can just assign 2 pointers to that. If the third step is our current pointer, then the one step before pointer is going to point to the second step, and the 2 steps before is going to point to the first step. Then inside of a loop, we're going to be calculating and updating these pointers. So this current position is going to be the sum of the 1 step before plus 2 steps before. So in this case, that's just 1 plus 2, or 2 plus 1, and we get 3. Now, the important part of this approach is updating the pointers, because if I moved on to this next spot now, if this was where my current pointer was, then 1 step before this would have to be where this 3 is, and 2 steps before this blue dot would be where this 2 is. And so, as part of calculating the current each time, we're going to have to update the pointers. So 1 step before is going to point to here, where current is, and 2 steps before is going to point to where the 1 step before was previously. And then we can update our current pointer, and calculate for the next step. And that's 3 plus 2, and that's 5. Update our pointers. 2 steps before is going to be where the pointer was, the 1 step before pointer was pointing before, and the 1 step before is going to be pointing where current is. And then finally, our current pointer is going to be where the answer is, the 5th step, and it's going to be the sum. 3 plus 5 is 8. We'll update the pointers, but the loop is going to end, and then we'll be returning 8, which is the answer. The time complexity for this operation is O of n, because we calculate or we iterate for n minus 2 steps, and it scales with the input size. The space complexity for this, however, is just constant O of one space, because we don't actually use any extra data structures. We just use pointers, and those pointers are going to be constant in space. Here is the code for our pointer solution. The first thing we're going to do is check if n is equal to 1 or 2. If that's the case, then we'll return 1 or 2 respectively, and we'll have solved our problem right away. If not, then we'll go ahead and continue with implementing our pointer solution. From the diagram, we saw that in order to solve for any step n, we'd have to know the sum of the two previous numbers. And in order to know the answers to those, then we'd have to know the two steps before that, etc. So essentially, we'd need to know all the numbers all the way up till n. And we're going to start calculating those from the third step because we know the answers for the first and second step. They're just the answers to our base cases. So my current pointer is going to be pointing to the third step, which I showed you guys in the diagram, and we've initialized that to null initially because we don't yet know the answer. So from our third step, one step before is going to be the second step, which the answer to that is 2, and from our third step, 2 steps before is going to be the first step, and the answer to that is 1. So we'll start off the loop at I equals 3, and that's going to iterate all the way till n. We're going to be calculating the sum from the two previous positions, and that's going to be assigned to our current pointer, and then my other 2 pointers, the 2 steps before and the 1 step before, are going to be continuously updated. At the very end, we'll return the current pointer because that's going to be pointing to the nth step, which we need the answer to. I'm going to run this, and it should pass our test cases. Awesome. Now I can give it a submit. And we successfully solved everything.